So we've talked about pulsating variable stars. It's one type of intrinsic variable star. There's other types of intrinsic variable stars. Besides pulsating, we have eruptive variables. And there's several different types of eruptive variable stars. Some of these eruptive variables have do different things. One of them is, for example, T-Tauri type stars. These are actually what we call protostars. They're stars still in the process of forming. They're still coming together to form the star, and so that star is magnetically active. It's unstable. It's still getting itself together, and so they get brighter and dimmer, and so they're going to be variable stars. Another kind of star that we'll talk about, Wolf-Rayet stars. These are stars that are very massive stars, very bright stars. They're very close to the Eddington limit that we talked about before. The Eddington limit, the brightest it can be before its light pushes the layers off into space. So Wolf-Rayet stars are also sometimes referred to as mass loss stars because they're actually pushing parts of themselves off into space. There's also luminous blue variables, which are very similar to Wolf-Rayet stars. Flare stars are something called UV Ceti stars, because one of the first ones discovered was the star UV Cetus, and so UV Ceti. And so this star, this is typically a red dwarf star, a very tiny little star that is very magnetically active. And so it turns out that red dwarfs are the most common kind of star that's out there, but they also tend to be very magnetically active to a large degree, and they have these supersized flares in which they can suddenly get hundreds of times brighter in just minutes. And then there's our Corona Borealis stars. They're really cool. We'll get to them in a little bit. Okay, so the UV Ceti stars tend to be these red dwarf stars. They get brighter, they get dimmer, but they typically are these little bitty dim red dwarf stars. And in this picture on the left, you don't even see it. Then suddenly it's there. Okay, they can be 2 to 5 magnitudes brighter with this giant flare. Okay, now the problem is if you happen to be on a planet surrounding this, then that planet likely just got sterilized, whenever this happens. So that's one of the issues possibly with finding life around a red dwarf star, is they might be sterilized by these occasional flares. Wolf-Rayet stars, these are stars that are very close to the Eddington limit, and some of them, like Eta Carinae, not too far away, used to be one of the brightest stars in the sky. It's faded since then, but when it was in the middle of an outburst blowing stuff out, it got super bright. Okay, now our Corona Borealis stars. These stars are downright cool. These are interesting stars right here. So our Corona Borealis stars are normally pretty stable, but periodically, or not periodically, just every once in a while, they suddenly dim down, then they get bright again. So they dim down and get bright again. So what's happening here? Well, these tend to be carbon-rich supergiant stars. And so what will happen is that these carbon-rich supergiants will, on occasion, build up carbon in the outer part of the star. Well, the carbon will stick together in these groups of 60 molecules called Buckminster fullerenes. And when the atmosphere, the outer part of the star, gets filled with these things, it starts blocking the light from the rest of the star. And so when you block the light from the rest of the star, then it dims down. Okay, and it can get dimmed down a few magnitudes, up to like 9 magnitudes dimmer in some cases. So they can get really dim. And then what happens, though, if the light can't get out, then the star starts to heat up. You start heating up, and you start breaking down these Buckminster fullerenes, but the carbon will actually recombine, and it'll form kind of a crystalline structure. Well, what's crystalline carbon? Yes, diamonds. Okay, so it forms these little diamonds, which it blows off into space. There's actually lots of diamonds in space. Most of them are little teeny tiny diamonds, but it's not uncommon for meteorites to have diamonds in them. And so whenever our Corona Borealis star is dimming down, just wait, because when it starts brightening up, it's spewing. So that was an example of the eruptive variables. And so now what we want to do is talk about cataclysmic variables. So those eruptive variables may have seemed, pretty impressive, but you can actually get even more impressive. I mean, you can actually get to where you're looking at something that's even more explosive than that. And so that would be the cataclysmic variables. So for example, a nova. Okay, with a nova, you have like a dead star, a white dwarf, and you have a living star and it's dumping stuff on the white dwarf, and then all of a sudden you have a giant explosion. That giant explosion can be 7 to 10 magnitudes brighter. Basically, it's a runaway thermonuclear reaction on the surface of the white dwarf. And so we'll talk more about how that works later. But the thing is that this is enough difference that you might have something that's too dim to be seen with the naked eye, and then all of a sudden there's an extra star in the constellation. Interestingly enough, a couple of novae were actually discovered in astronomy classes. In particular, there was a nova in the constellation Cygnus back when I was just starting astronomy. That first day of the semester, professor had an astronomy class out in the dark and was pointing out stars in the constellation Cygnus and realized there's an extra star in there. And that was the discovery of nova. And so some novae just happen one time. Sometimes they happen again after decades or centuries or something. But there's another type of thing that's like a dwarf nova. Again, it's a white dwarf star, stuff spewing onto it, explosion, but not as big of an explosion. And that's what we call an SS Cygni star. Because the first one discovered was named SS Cygni. And so these are like miniature novae that happen every week or so. Well, when Walter Baade was working in the U.S. for the first time, he teamed up with a fellow named Fritz Zwicky, and they were studying novae, and they realized that some of the novae that they were discovering were super bright. They would get 20 magnitudes brighter or more. And so that's an enormous increase in brightness. Remember, every 5 magnitudes is 100. So this would be 4 of those. So 100 times 100 times 100 times 100. Okay. So that's amazing. That's 10 million times brighter. And so he realized that nothing could survive that. That would so far exceed the Eddington limit, there'd be no hope of a star surviving. So he realized what he was actually seeing was a star exploding. So a supernova is actually an exploding star. We'll get more about how that works later on. So a supernova explodes. Now, of course, if there's any planet there, poof, the planet's gone. I mean, a supernova is going to be so violent that if a supernova were to go off anywhere within 10 light years of us, then we would have massive environmental damage to the Earth. And it would make complex life forms like humans difficult to survive. So these are incredibly huge explosions. One of these was so bright, it was visible in the daytime. In the year 1054, people looked up and they saw an extra star up in the daytime. At night, the star was so bright you could read by the light of the star. And so it would cast shadows at night. And so Baade was able to pin down where this was in the sky. And where it was in the sky turns out to be exactly the same spot that Messier number 1 is located. The first thing on Messier's list, what we call the Crab Nebula. Now, interestingly enough, Messier lived a few hundred years ago. He recorded this object as being really bright. Nowadays, it's not nearly as bright as it was when Messier saw it, so it is gradually getting dimmer. Okay, again, indicative that we had something that actually blew up like 1,000 years ago, and so so we have evidence here as to kind of what the supernova would be like.